Okay, so we are going to find the deflection of a beam now using the method of superposition. So the method of superposition says that if you have multiple loads acting on a beam, you can find the deflection of the beam from each of these loads separately, and then to find the deflection caused by both of these loads acting together, you just add up the deflection caused by each of these loads acting separately. You sum those effects together, and that will give you the total deflection of the beam from both loads acting simultaneously. So here we're going to look at another cantilever beam, and we're going to determine the deflection at the free end of the cantilever beam if the free end is subjected to a force F and a moment m0. Okay, so we already know, we've already seen what the deflection is going to be due to this force F. So just to remind, we know the following. So from F, we know that the deflection caused by F at the free end of the cantilever beam is equal to negative FL cubed over 3EI. And again, the length of our beam is L. Modulus of elasticity E, moment of inertia I. Okay, and then the deflection downward is negative, upward is positive. Alright, so we already know what one of the deflections is, caused by F. And now what we need to do is find that the deflection is caused by m0, and at the end of the problem we're going to sum up the deflection from F, the deflection from m0, and then that's going to tell us what our total deflection is when both of these loads are acting simultaneously on the beam. So we're going to follow the same process. We're going to use the method of integration in order to find what the deflection is due to m0. So remember, to use the method of integration, the first thing we need to do is come up with an expression for the moment as a function of position on the beam. So what we did last time, we drew a shear diagram and a moment diagram. So the shear diagram helped us draw the moment diagram. So just to make it clear though, we are right now just going to look for the deflection caused by the moment m0. Okay, so if we have a free body diagram, we have our beam, we have a moment applied on this end, that means we have a reaction moment m on the other end. So you can see, just by inspection, we'll do it formally. If we sum the moments about, we'll call this point A again over here. If we sum moments about point A, then we're going to have that m minus m0 equals 0 and m equals m0. Alright, so that's not a surprise. You can kind of see it just by looking at it. Yeah, so we get that m is equal to m0, and then we draw our shear and moment diagrams. So our shear diagram, there's actually nothing there this time because we don't have any shear. So when we just have an applied moment, there's no reaction load. So when we draw our shear diagram, there's actually nothing happening. We just have 0 all the way across the beam. Because there's no applied shear forces, there's no reaction in that direction, so there's nothing on our diagram for V. We go to M, so this means the slope of M is going to be 0 since V is equal to 0. So we get that our moment is equal to m0, and since it's positive m0, that means on our moment diagram we come down to the negative side. So we have a negative m0, and we stay negative with a slope of 0 all the way till we get to the end of the beam, and then we come back up to 0 because there's an applied moment of m0. Okay, so from this we have that our moment equation as a function of x, we can see just by looking at our moment diagram, we use the moment diagram to write our equation. We have that m as a function of x is just equal to minus m naught. Okay, so now we're going to go ahead and follow our method of integration to write to derive what the equation is for the deflection of the beam as a function of x. Let's make a little room for ourselves. So we know that this relationship is known EI d squared v dx squared is equal to the moment, and then we just said that our moment is equal to minus m naught. That's our expression for moment as a function of x. So we go through the process of integrating twice. So we have EI, this is our first integral, is dv dx, and that's equal to, now we integrate the right hand side, we have negative m naught x plus a constant integration, call it c1. We integrate again, we have EI times v equals minus m naught x squared over 2 plus c1 times x plus another constant of integration, we'll use c2. Alright, now this is a cantilever beam, so our boundary conditions we know are that at x equals 0, this is at the fixed end, boundary conditions at the fixed end, we have at x equals 0, we know that v equals 0 because it's a fixed boundary condition. We also know at that same spot at x equals 0, we know that the slope is equal to 0, dv dx, again since it's a fixed boundary. So we're going to, and if we call this equation 1 and call this equation 2, we're going to sub these boundary conditions into equation 1 and 2. So let's start with equation 1. We're going to sub in the boundary condition that dv dx equals 0 when x is equal to 0. So subbing that in is going to look like EI dv dx is then 0. So EI times 0 minus m naught times x, when x is 0 is just 0, plus c1. This gives us our first constant of integration, c1 is equal to 0. And then our second constant of integration we'll get from using equation 2. So EI, we know that v is 0 at x equals 0, so it's EI times 0 is equal to negative m naught x squared over 2, x is 0, so that's just 0. The second term, c1x, x is 0, so that's 0, plus c2. So we have that our second constant of integration is equal to 0. And so given that, we can then write our expression for the displacement. So we have, now that we know that our constants of integration, so if we plug our constants of integration, which are both 0, back into equation 2, we have EIV equals minus m naught x squared divided by 2. And if we'll rearrange it so that we have an expression just with v on the left hand side, and we have minus m naught x squared divided by 2EI. And we want to know what the deflection is at the tip, so we're then going to plug in L for x. So v at x equals L is equal to minus m naught L squared divided by 2EI. Okay, so this is our intermediate answer. So we just derived what the deflection is going to be at the end of the free end of the cantilever beam due to a moment m naught. Okay. We want to know what the total deflection of the beam is though, from the caused by the force and caused by the moment. So this is where we're going to use superposition. So by superposition, let's try that again. So by superposition, we have that V, the total V at x equals L, and actually just up here coming up a little bit, I'm going to give this V the subscript m naught. So we know that that's the V caused by m naught. The total V at x equals L is going to be equal to the V caused by the force F in addition to the V caused by the moment m naught. And then we just sum up the two expressions that we've derived. So we have V at x equals L is equal to minus FL cubed over 3EI plus this expression for V caused by m naught, which is we're going to add a negative, so we'll have minus m naught L squared over 2EI. Okay, and then this method will work for any different kind of deflection equation. So any load, whatever deflection it causes, you can find the individual contribution of each load and then add them all together to get the total deflection at the end.